Welcome in the class of engineering mechanics. This is lecture 8 of unit 5th. Today we are going to discuss virtual work method. So, virtual work method is if a small displacement in the form of virtual is given in a system of forces acting on the bodies, then the total work done by the system is 0. Okay. Suppose I have a beam. Okay. Suppose I have a beam and okay, and it is subjected to certain loads. If it is subjected to certain loads, okay, due to certain loads there will be a reaction, say R A, say R B. Okay. If we apply certain virtual displacement, okay, means say this is A, this is point B. Okay, say if I am going to take this virtual displacement like this. Okay, so the in this case the deflected shape is this. Okay, so this is virtual. This is virtual displacement. Okay. This is virtual displacement. It is not actually, but this is the virtual. Okay. So, here if okay, point load is acting here, so it is P, say it is Q. Okay. Okay. Say if this ordinate is y1, this ordinate is y2. Okay. This ordinate is y2. Okay. Say this is RB. Okay. This is RB. Okay. So, this point is A. This point is say okay, let me okay, this point is say this point is say B. Okay, this point is say C, this point is suppose D. Okay, so C D. Okay, this point is D, say this point is E. Okay, so point force P is acting at point E, force Q is acting at point D. So, and this one, say this is y3 and B, okay, the roller support is here, A at A hinge support is here. So, if I give this displacement, okay, say for any amount, say this is this is value any delta, okay, any delta, then total work done, if this system, okay, if this system of forces, what is the system of forces? System of forces are R A, R B, okay, this point load P Q, this is the system of forces. Okay. If this is in equilibrium, then work done by all the forces, that will be 0. Okay, that will be 0 for this virtual displacement. Means what we can write here. Okay, we can write as R A into R A into 0. R A is not going to contribute any work done. Why? Because the displacement at this point is 0. Okay, plus this one force, it is acting in downward. Okay, so it is acting in downward. So P minus, okay, y1. Okay, so this point load force, it is acting downwards. That's why we have taken so that's why the work done contributed by this force, this will be minus y1. Okay, so this is the work done contributed by this one force. Okay, next force is this one, reaction at point B. Okay, so plus RB into what is the ordinate at this point? Ordinate at this point is what? It is y3. So, and it is in upward direction. Okay, that's why we will take positive sign. Okay, what is the next force? Next force is this Q. So, plus q into, and what is the ordinate at this point? It is ordinate point is y 2. What is other remaining force? Is there any remaining force? No. So, equate it as 0, equate it as 0. Okay. By equating this, we can calculate the value of R B. We can calculate the value of R B. We can calculate the value of R B. Okay. Similarly, if we will, displacement, okay, if the displacement is given by delta at point A, okay, then the deflected shape will be this, deflected shape will be this. Okay, okay. Care must be given that in giving the displacement, okay, in giving the displacement, geometry should remain same. Okay, means that can be rotated at any point. Okay, so no problem, that can be possible. So, if we want to give the virtual displacement delta at point A, then this will be the shape. Okay. So, the ordinate, corresponding ordinate, okay, R A into delta, P into this ordinate whatsoever, okay, say, and R B in 0, okay, here Q into this one ordinate whatsoever is the ordinate, that equals to 0, and by doing that we will able to find the value of R A. Value of R A can be determined, value of R A can be determined. Okay. So, the virtual work, okay, if the equations made by virtual work, they are sometimes the same equation as we did, as we write the equations by using static equilibrium equation, we get the same result, but different equations can also be written. Okay. So, this is the method, this is the method where we will not use, where we are not going to use any static equilibrium equation, but we are able to calculate the parameter, different parameters, right. So, this is the basic idea, and for better understanding we will solve few questions. Okay. Okay. One more thing, if at any point, okay, if suppose if there is a moment, then what we will do? Okay. We know that moment, work done by the moment, it is moment into displacement, for nothing to worry. Okay. Moment into displacement, what will be the displacement, that will be applied. Okay. Say we are giving this displacement. Okay. So, the what is the rotation here, that we can calculate. Okay. If theta is there, okay, if theta is this, so we same theta is here, so calculate. Okay. If y is the vertical displacement, so whatsoever is the value, that we can calculate. Okay. So, let us do one first example. In this example, we have 3 set of forces are given, 50 kilonewton, 80 kilonewton and 70 kilonewton. They are acting at a point, okay, and we need to find the resultant, using virtual work method. Okay, that question can be done by static equilibrium equations, no problem, but we will do it by virtual work method. So, here we need to apply virtual displacement. Okay. Virtual displacement need to be applied. Okay. Since this point, okay, it is in x and y plane. If I am writing this as x plane, if I am writing this as y plane, okay, that is why this point O can translate to any point in this plane. Say this is the translation, from O to O dash. Okay. So, if I am giving virtual displacement and delta x, and this as horizontal virtual displacement in x axis at delta x, and in vertical say this is del y, okay, as shown here, okay, a horizontal and this is vertical. Okay. So, this is the say this is the funnel, okay, this is the funnel. Okay. So, suppose we have okay. So, we will make we can make two equations, for horizontal, for vertical, okay. And you will see that we need only two equations, to find the resultant of this force, okay, to find the resultant of the force, okay. And so, let us do okay. One more thing is that in the previous definition, a small displacement is given in a system acting on the bodies, okay, system of body work done by the system is 0. Equilibrium, okay, must be in equilibrium, then it will be 0. Okay. So, how to make how we can make this as this in equilibrium conditions. Okay. So, if we have the force, okay, we have the force in say in this direction, okay, in this direction, component of force in this direction, then what we need to do? We need to apply the force in this direction to make the resultant 0. So, we will do this one here. Okay. So, let us do for horizontal translation. Okay. Let us do for horizontal translation. Okay. So, for virtual translation, for virtual displacement, del x. Okay. For virtual displacement del x, what we can have? Okay. This one force 50 kilonewton force is acting, it is inclined at 45 degree. So, it is a horizontal component, it will be 50 cos 45 degree, right. It will be in x positive action. So, positive sign here we have taken, and it will be multiplied by del x, right, plus 80 kilonewton force, it is inclined at an angle of which one? 25. So, plus 80 into cos how much? 25 into del x plus, right. This one force 70 kilonewton force, it is inclined at an angle of 25 plus 25 from horizontal. So, it is a horizontal component, it will be 40 cos 50 into del x. Okay. 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 So, this is the value. Okay. Say let us apply a force, let us apply a virtual force to make this body in equilibrium. Okay. Say we have applied this one virtual force, this is this is okay. If we need to find the resultant actually, yeah. Say okay, if virtual, okay, say this is E, okay, this is the resultant, okay. No, this is say we had applied the force E, okay, at an angle of certain theta, okay. So that this the force acting at the point O turns into equilibrium, okay. To make the system in equilibrium, we applied a force say E, okay, force say E, okay. So, plus we will write E into cos theta, okay, that equals to 0, that will equals to be 0, that will equals to be 0, okay. Therefore, therefore, okay, into del x into del x into del x. So, you can see from here that you can find the value of E cos theta. You can find the value of E cos theta, and when you will find the value of E cos theta, then it will be 152.86 Newton. After calculating, you will get this something. Okay. It will be in minus sign, because all the forces are acting in positive direction. E cos theta. Okay. E is the force I am writing here to make the body, to make the system in equilibrium. To make the system in equilibrium, we apply a force E. Okay. You can write F also, no problem. Okay. So, by doing this, we get the value of E cos theta. Okay. Similarly, for virtual displacement, del y, for virtual displacement del y, we can write one more equation. Okay. So, what will be the component? Vertical component will be what? 50 for 50 Newton, it will be of 50 into sine 45 into del y, right, plus what will be vertical component of 80 sine 25 into del y, oh right, plus 70 sine 50 into del y. Okay. So, these are the component, vertical component, plus E sine theta equals to 0, because the body is in equilibrium. Therefore, value of into dy, okay, into dy. Do not forget to multiply the virtual displacement. So, value of E sin theta can be calculated, and after solving you will get 52.07 Newton minus 52.7 Newton. Okay. So, these result will give you the resultant. Okay. From here, look, if we will apply the force, okay, E in this direction, is it possible to make this force in equilibrium? No. Why? Because it is in the in this direction, therefore, that is why in opposite direction. Okay. So, F component, F cos theta, in spite of having in x direction, it should be in negative x direction, and y component in negative direction. Okay. Therefore, if R is the resultant, so if R is the resultant, if R is the resultant, okay, then we then R will be equal to, if this is E, then this will be the R. Okay, then this will be the R. Therefore, R cos theta, it will be 152.86 Newton, and R sin theta, it will be 52.07 Newton, right. Now, you can calculate the value of R. Okay. You can calculate the value of R. Okay. This okay. So, resultant will be this R and this theta. You can calculate both the value. So, R you will get after calculation 161.48 Newton, okay, and value of theta, it is coming as 18.81 degree, okay, from x, that you can calculate using virtual work method. Let us do one more example. Okay. Here okay. So, simply supported beam is given to you, 2 point loads 20 kilonewton and 40 kilonewton is acting in the beam, okay, in the acting beam of length 2 meter, 2 meter, 2 meter, 2 meter, total length is 6 meter. So, here it will be R A will be here, here it will be R B, okay, will be R B. Distances are shown 2, 2, 2, okay, equal distances are shown here. Okay. We need to find value of R A and R B. We need to find the value of R A and R B not by using equilibrium equations, not by using equilibrium equation, we will find using virtual work method, right. So, 2 unknowns are here actually, 2 unknowns are here, unknowns R A and R B. Therefore, we need to give 2 virtual displacement, we need to give 2 virtual displacement, right. So, let us provide the virtual displacement at point B. Okay. If it is del y, okay, if it is del y, okay, if it is del y, then what the component of this will be under the load of 20 kilonewton and 40 kilonewton, that we can calculate by interpolation, linear interpolation, right. Similarly, if we will give the displacement del y dash, okay, del y dash, okay, then the component can be calculated, okay. And for both we will have two equation, we can write 2 equation, oh, we can write 2 equation, means work done, this system is in equilibrium, if this system is equilibrium. So, work done by this virtual displacement, that will be 0, okay. For this one means we can write 2 equation, we can write 2 equation. How? You see here, first of all, okay, displacement that has been shown here, okay. So, it will, okay, it is better displacement under the point load that has been mentioned here. So, and that can be calculated by linear interpolation. How? Linearity, how? Del y by total 6 is equal to this one distance divided by 4, this one distance divided by 2. So, you can calculate the value of that ordinate, okay. So, let me make equations, okay. This is for 1, okay, say for 1 for virtual displacement this one, okay. So, here displacement at point A, it is 0. So, R A into 0, okay, right, plus this one 20 into vertical displacement, it is since it is acting downward. So, we need to put minus 1 by 3 del y, okay, okay, del y, okay. You why you need put either del y or del, no, it does not matter, okay. So, and another force 40, okay, plus 40 and displacement downward, okay, displacement upward and force is acting downward. So, it is again minus 2 by 3 del y, right. Another force R B, it is in upward direction and virtual displacement we have given in upward direction, that is why plus R B into which one, del y, equal to 0, is equal to 0, okay. No any other force is acting in this system. So, equate it as 0, right. So, R A, so a value of R B can be calculated very easily, value of R B can be calculated, okay. Del y will be cancelled out, okay. So, the value of R B coming in this after calculation, it is 33.33 kilonewton, 33.33 kilonewton, okay. Similarly, writing the virtual work equations, okay, for this case 2, okay. So, what we will get? We will get R A into del y, okay. So, for case 2 this is R A into del okay, del y dash, say del y dash plus plus 20 plus 20 plus 20 times of which one ordinate, it is 2 by 3, okay. It is minus 2 by 3 del y dash, right, plus this one force 40 into minus 1 by 3 del y, right, and this one at point B no displacement is no virtual displacement is here. So, R b into 0 is equal to 0. So, from here we will calculate the value of R a, okay. We will calculate the value of R a, it is 26.667 kilonewton, okay, kilonewton, okay. So, in this question we also not did not use any equilibrium equations, and we have calculated both the values R a and R b, okay. What is the summation of these two? R a plus R b, it is going to 33, it is 60, okay. Equation is satisfied. Summation of R a plus R b, that is equilibrium, okay, it is in equilibrium. So, this is the virtual work method by which we can calculate the parameters, okay. Say in this example, what the virtual, how many parameter we need to find here? We need to find here 2 parameter, okay. We need to find 2 parameter R a and R b, okay. And from here which one parameter, if I am giving the virtual displacement at this, okay, del y, okay, then based on the length, based on the distances, okay, the ordinates are shown in this diagram, okay, is 2 del y, okay. And which one reaction we will able to find from this virtual displacement, okay. It is a very obvious that we can calculate the value of R b, we can we can calculate the value of R a, okay, because we do not have any virtual displacement at this point, okay. So, and one more thing, okay, by providing this virtual displacement, the geometry of the beam remains same, okay, it is not going to alter, okay. So, by applying this we can write R a times of 2 del y, right, it is in okay, as per this sign convention it will be of minus, okay. So, put it as minus plus okay, here it is UDL, okay, here it is UDL. So, UDL it is 30 into 6, it is the point load, and this point load is acting where, at the midpoint. So, the work done by this this point load, okay, this equivalent point load, it will be 180 times of del y, okay, and it is also since it is acting, okay, it will be plus here, okay, because it is acting downward, okay, and displacement is also downward. So, it is minus means positive, right. R b, it is not going to take any part, okay. So, R b into 0, okay, plus 20 into del y, okay, minus sign will be taken, okay. So, value of R a can be calculated very easily, and its value is 80 kilonewton. Its value is 80 kilonewton, okay, without using any equilibrium equations, okay. So, if you want to calculate the value of R b, if you want to calculate the value of R b, then what can be the which type of displacement you can provide, this virtual displacement you can provide, okay. Say this is delta, and find the ordinate, okay, find the ordinates, then write the equation, and then calculate the value of okay, this is actually same thing, I made the same thing, okay. No, it is better to give this, okay, to this, okay. So, by doing that by doing that, okay, this is thing, this is thing, okay, this is the virtual displacement, okay, this is the virtual displacement, okay, that and that is no difference, okay, here so yeah, this displacement, okay. So find the ordinate, find say this is any certain distance, certain virtual displacement. So find the value of ordinate here, here, okay, here it is 0. So value of R A can be calculated, okay, value of R A can be calculated, okay. At the last here it is a hinge, okay, it is the hinge, okay, and we need to calculate the support reaction, okay, this one, this one 3, okay. So it is a determinate, actually it is a determinate, okay, because 3 unknowns are here and 1 internal hinges are as here, okay. So the virtual displacement can be given, virtual displacement can be given in this manner, virtual displacement can be given in this manner, okay, because this is part 1, this is part okay, this is part 1, this is part 1, this is part 1 and this is part 2 type of thing, okay. So internal hinge, you know very well that this is internal hinge like this type of thing. When you will apply the load, then it will move in this manner. So this virtual displacement that you can give, okay, by del u can apply. So you can calculate the value of, from here you can calculate the value of which one, you can calculate the value of R A, you can calculate the value of R A, okay, you can calculate the value of R A, and after calculation it will be 12 kilonewton, right. So this is the method how you can calculate the value of any parameter. So in display in truss you can also apply, you can also apply, right, you can also apply what if the force in this member is required, okay, force in this member is required, then what we need to do, we need to apply, we need to give certain displacement, okay, certain displacement d theta, and due to that find the forces and write the work done equation to calculate the values, okay. So reference book, okay, and thank you very much for the listening, okay, thank you.